going to have an equal representation of all the sections we covered. So nothing's going to be emphasized or de-emphasized, really. Well, it looks like we've got about a half a minute. Any questions so far, folks?
I was curious, just logging in. What is the history of calculus? Are we still developing calculus, or is this pretty
In
much
certain
like a hard in science, and it was developed in the 1600s or something like that?
So the calculus we're doing, single variable calculus, is just like you said. It was discovered by Isaac Newton and Leibniz independently in the 1600s. But the calculus that people are working on these days is a little bit different. So different things are still being developed, and let's see. People are working on stuff that goes like this: differential calculus on manifolds. Sounds crazy abstract. It's not too unfamiliar. See if there's an image. Nothing great, but yeah, there's lots of stuff being developed in this idea, differential geometry. They're still looking at things like rates of change, slopes. Instead of tangent lines, you might be talking about tangent planes, kind of related to Calc 3. But there's plenty of research, open questions going in all directions in this kind of stuff.
I was talking to a guy and he's trying to get a math education degree on this random school, like over the internet. But they have to take Calc 1, 2, 3 in this class called Advanced Calculus. What would the Advanced Calculus be if he's already taken 1, 2, and 3?
So the question was, if you've taken calculus 1, 2, and 3, the full sequence, and someone in math education is being asked to take advanced calculus, what is that? I bet you it's not hard to say exactly, but it's probably vector calculus. That's hard to spell, but he's probably looking into vector calculus for advanced calculus. And what happens in vector calculus is you just pick up right where calculus 3 left off on. Calculus 3 really isn't quite finished when you finish the class. In fact, there's tons of stuff in the same directions where it leaves off. And you start just doing more stuff like this: dot products, cross products, different kinds of vector products, using more and more linear algebra all at the same time. So that's pretty much what advanced calculus is. Very related to what Chris was asking about with other kinds of calculuses you can do. For example, all of this is along the same lines: advanced calculus, calculus on manifolds, but you can define something like this: a torus. So there's our torus right here. And instead of doing calculus on a plane like we're doing, you can imagine everything is on this right here. Maybe instead of a torus, it could be some completely different other type of geometric object. And you still want to develop what would calculus look like if all of your objects are constrained here instead. So that's what those kinds of subjects are trying to get into. But other questions so far, folks?
So that last example is similar to like changing a coordinate system, right? You're going from an XYZ to a torus, whatever that would be.
Yeah, exactly. You're doing a change of coordinates, and that's another big part of calculus as well. Absolutely. Sometimes we're doing calculus on a torus, sometimes it's just on a disk. And each time you change where your actual sample is or your domain, you have to do some kind of crazy change of variables, different perspective on it. But that's all pretty cool stuff. What's weird about calculus too is we're doing those same kinds of things in chapter 7, still the same kinds of things in chapter 8 and chapter 9 when we're doing, say, applications and differential equations. But chapter 11 is like its own thing: power series, Taylor series, Maclaurin series. So this is the one aspect of calculus where we're kind of shooting off in a different direction temporarily until calculus 3 reels it back in. Well, any other questions so far, folks? Okay, these are always fun questions. And with where we're at so far, we're most of the way through 11.6. I think we're more than halfway. Then we're going to start looking into power series. Like I mentioned, this is pretty abstract in its own way, but it does have really good reasons why we'd be wanting to look into power series. For example, if you're wanting to, say, integrate this function, we don't have a lot of great tools. We can use trapezoid rule, Simpson's rule, for example, but what we can't use is the fundamental theorem of calculus directly because we can't produce an antiderivative to that thing. Our author mentions this, that there is no closed form solution to that. However, power series can do it. The only trouble is you need to take the function y equals e to the x squared and represent it this way. Summation as you go from 0 to infinity, Cn times x minus a to the power of n. So we're going to take a function that's totally fine, but has problems with an antiderivative, and represent it as some kind of power series. So that's where all this is trying to get back into, finding a decent antiderivative. Well, with what we're going to get through in section 11.6, we're finishing off our last tests. Then this is the major punchline to chapter 11. Well, it's the start of it. 11.9 is really just that part 2. And then the major capstone is section 11.10, Taylor series and Maclaurin series. So we're getting on through it. And also, before I forget, we do have a class cancellation tomorrow, only because it's Halloween. And I found that doing class on Halloween just means not a lot of people show up, which means most of the class gets a little bit more behind. So we're going to treat tomorrow as really just kind of a catch-up review day. I'll still have office hours available, so I'll be taking emails as available, but we won't hold class officially. I think that's my full set of announcements. Any additional questions or comments before we jump back into the notes? Okay, so let's take a look. We're in section 11.6. And in this section, we are developing 2 new types of tests. The first one, let me see if I can pull this up, is the ratio test. Ratio test is fantastic in that it has 3 outcomes, really easy to use, and the outcomes are very powerful conclusions. Absolute convergence on one, divergence on the other. It just has a time where it's inconclusive and the test can fail. What we did on the last problem was we used the root test. The reason we use the root test is this series has a 5 to the power of n, and dealing with that is not easy with the ratio test either. The algebra just kind of blows up on us. But if you can eliminate that power n this way by taking an nth root as n goes to infinity, then the process becomes a lot more simplified. We broke down 5 times n in this way. Exponents say they would multiply back together. And then when we took the nth root, that power of n just is eliminated. And that's the rest of the steps. Just take one more limit. Came out greater than 1, and that's our condition for divergence on this one. So we'll try it out again and see how it goes. But any questions on this quick rundown of the ratio test here? Okay, for our next one, we're going to use a ratio test on this thing. Our hope of hopes is that we can write the sequence somehow like this, or excuse me, not quite like that, somehow like this. We want a common power n as the outer power and something on the inside being raised to that power. And that means we need to do a little bit of work on the exponents of this thing. So let's start off by just calling it summation an, so it has a name. Then an, the nth term, is 2n plus 3, but we can deal with the plus 3 by going 2 cubed times 2 to the power of n. Then down below, it's n plus 1 power of n. We don't need to do any changes on that. We can write this whole thing as 8, 2 over n plus 1 to the nth power. This n power would go back on 2, go back on n plus 1 if we were to raise the numerator denominator to that power. So that's one way to rewrite this series. And that's really helpful because now we can say this thing is equal to summation and goes from 1 to infinity of 8, 2 over n plus 1. That 8 is kind of pesky being right where it is, but you can do another thing on this. Convergence or divergence of this entire series right here is not determined by multiplication by 8. So we can take that 8, move it outside. The summation as n goes from 1 to infinity of 2 n plus 1 to the power n. So we're going to test this series here, leaving the 8 factored out. If this converges, then so does the original one with 8 distributed back inside. So I guess we need to call this a new name. This is 8 times summation. Well, we already have an, that's the total series, but we're going down to the next series, bn, where this one is just referring to that part. So the way we're going to test this is ignore the constant and see if this portion converges or diverges. Well, we're through the rough part. We've got the exponent right out here wherever we need it. And now when we go to use the root test, here's all we really have to write. We take a limit. N goes off to infinity of nth root, absolute value. Saying an is not a huge mistake as long as you use the right thing over here, but being more careful, we'll use bn. So let's expand out the limit. It's now a limit as n goes to infinity of the nth root. When we go to take the absolute value of bn, nothing happens. This is always positive, every single one of these terms. So we'll just not worry about the absolute value. We'll drop it and just copy this in 2 over n plus 1 to the nth power. Now everything is working as designed because the nth root cancels that nth power, and we don't have anything causing weird kind of issues like dealing with the 2n plus 3 could be a problematic issue for us. Instead, we're just taking the limit as n goes off to infinity of what's left over, 2 over n plus 1. That's a nice limit to take advantage of. We have degree 1 in the denominator, degree 0 in the numerator. So as a rational function, it has a horizontal asymptote of 0. That's exactly equal to the limit since we're going off to infinity. Now, we'll check our notes. This is our brand new test, but it has the same conclusions as the ratio test. That's really helpful. If your limit is less than 1, then your series was absolutely convergent. So we'll say here, therefore, summation, well, this one's absolutely convergent, but if this converges, multiplying by 8 doesn't change the convergence or divergence of the original one. So we'll go for the larger conclusion. an converges absolutely. Deserves an exclamation mark because, again, that's not a lot of work for getting that kind of conclusion, absolute convergence. Well, any questions, folks, with the write-up of Part B? Okay, when we're in the next section, 11.8, the test we're going to use the most is the ratio test. This gets used practically all the time, but when the root test is relevant, it's like the only thing you can really use. So it's going to come up a couple times in 11.6, but don't forget about the root test. We don't use it a lot. It will come up, let's see, in this assignment here, exercise number 14. So that's the hint on this assignment, the next one. Well, now that we've done those, my next example here is really just kind of a review of what we've been doing so far. We're going to look at the ratio test, root test, and whichever other tests we need in order to determine absolute convergence, conditional convergence, or divergence. These problems are kind of tricky, but keep in mind, ratio test or root test already gives that conclusion, converging absolutely. Well, any questions at all, folks, before we try our Part A? Okay, so looking at that, that just looks like a total mess of a series. There's always a kind of a giveaway to some of these. If you see a factorial, that part right there, this means ratio test is effective. So with the n factorial there alone, that would be the test I would go for. You might ask, why not just use test for divergence? Well, there's trouble with that test in that calculating a limit with a factorial is not straightforward at all. So if you can avoid it, it's probably a good idea. So this limit is tough, but somehow, some way, if you use the ratio test, that's actually an easier limit. It's kind of a surprise. The reason for that is if you take the successive term, an plus 1, divide by an, what happens to make the limit easier is there's tons and tons of cancellations. You're not working out this entire thing in a limit, which is convoluted. It actually simplifies on us. So let's give this a ratio test approach. In the ratio test, it doesn't hurt to organize a little bit. So you might want to say an plus 1 equals this, but in place of n, we throw in n plus 1. It's going to turn into -1, n plus 2. That's kind of weird to write, but it's totally mathematically correct. In place of n factorial, we have n plus 1 factorial. In the denominator, it's 10 power n plus 1. Now that we have that, just in case it's helpful for visualization, let's just write out an. An is this with no changes. So we're just copying -1, n plus 1, n factorial, and 10 to the nth power. Next, we just put those together inside a limit, and we're on our way. Take the limit as n goes off to infinity of the absolute value of the successive term. An plus 1 must always be in the numerator for this process, and an must always be in the denominator. So if we take that limit, we're writing out limit as n goes to infinity, absolute value of. First, we have a big fraction coming from this right here. So it's -1 power n plus 2. The n plus 1 factorial part simplifies on us. N plus 1 factorial can be rewritten as n plus 1 times n factorial. Let's pause right there since this is kind of confusing, I think. We're not too sure how it goes. Any questions, folks, on the yellow highlighting, how we got to that part? Okay, so with that simplification there, let's go to the denominator and break this down a little bit. If we factor, it's well worth it, helps to cancel. This is 10 times 10 power ben. And then we multiply by the reciprocal of an, since it's in the denominator. So now it's 10 power ben, divide by -1 power n plus 1 n factorial. Now, this is the fun part. We get to do all of our cancellations. First off, 10 power ben is gone. And notice the thing that makes this limit tricky, n factorial, it's totally gone as well. That's why the ratio test is so powerful. It can take a factorial function and totally eliminate it in that way. And what do we have left? Well, there's absolute values in the problem, so it's eliminating these things all as well. Not too many survivors there. We're now taking the limit as n goes off to infinity of, let's see, this survives, but it's always positive, so absolute value does not affect it, n plus 1 over 10. I think that's pretty much it. As n goes off to infinity, the numerator explodes while the denominator stays finite. So this one is infinity in its limit. If you get infinity, for some tests, that's actually pretty bad, like, say, the limit comparison test. But in the ratio test, this gives us an immediate conclusion. We can say, therefore, summation an, referring to the original one if we forgot to put that on there. Let's put it on there just for good measure. What would you all say is a conclusion? Converges or diverges?
Diverges.
Absolutely. If it's going off to infinity, then as you said, this diverges. So we're done. There's nothing further to do on that one. But notice it also kind of resolves a question you might have had in your back of your mind. What grows faster, the factorial or the exponential? Looks like we're saying the factorial. Otherwise, if the factorial was in the denominator, we should have gotten convergence. The reason it diverges is factorial grows so fast in comparison to even an exponential function that there's no meaning to this total sum. It just diverges off to infinity. So this one's kind of just a review of the ratio test, really. These are not always easy to pick out. Like, for example, on this one, we wouldn't want to use the ratio test at all. But a really good question is, why not? What goes wrong? Let's just use it and see what happens. So this one is going to be an example where it's kind of a misadventure, but it's just as important for us to know when things go wrong, so we know when to switch gears and try something else. So let's call this first attempt. I should spell that right, though. We're using ratio test. So for using ratio test again, here's how it should go. Limit as n goes to infinity, absolute value, an plus 1 divided by an. We'll still use color coding, but let's just write it out directly this time. Limit as n goes off to infinity of an plus 1 means take all of this, but add 1 everywhere n occurs. So it's -1 power n. Denominator is kind of annoying. It's 3 times n plus 1, so we want to simplify that next. Finally, all of that is an, so we don't change the index. Since we're dividing, we just take its reciprocal. 3n plus 1 divide by -1 n minus 1. So this is what happens if we use a ratio test. Nothing really concerning so far, right? Everything just looks like a normal limit. We even have some great cancellations. The alternating part of this series is gone, those terms. So now it's limit as n goes to infinity. Let's see, we can drop absolute values because all these portions that survived are positive quantities. 3n plus 1 in the numerator. The denominator after distributing is 3n plus 4. But we know how to take that limit. This is, once again, another rational function. Doing this limit is different from this one. This one was a degree 1 in the numerator, degree 0 in the denominator. That's why it went to infinity. But this one has a tie in degrees. That means the coefficient of the highest degree term in numerator and denominator forms the limit. This forms the horizontal asymptote, in other words. So it's 3/3, coming out as a 1. But there is our problem, folks. If we're using the ratio test, that's really, really bad news. We want anything but a 1. We need it to come out positive, too. We have to remind ourselves of that. But in the ratio test, if your limit comes out as 1, the ratio test has failed in the sense that there's no conclusion, or in other words, it's inconclusive. Our series could converge or diverge. We just don't know yet. So from this part right here, ratio test is inconclusive. Well, that kind of sucks. That means we did all this work for nothing, but that's okay. Imagine, however, if this was a real exam question, maybe you don't have enough time to erase all that and do another attempt. Just leave it there. That's something we tried. It's still worth credit. I mention that because sometimes people erase everything and don't put anything else back down. Unless you have time to rewrite something, even to leave an attempt, even if it didn't go out right, that's still worthy of having something down on paper. Well, if the ratio test fails, we have to think of something else. Lots of things we can try. Any volunteers for something we could go for? Turns out that would be the right test on this one. So alternating series works because it is in fact an alternating series. Means this one's more of a review problem, really. So let's say second attempt. Alternating series test, as you suggested. So let's take a look. For using the alternating series test, that means we're going to let Bn, just trying to pick a color. I guess we'll go with just black. No, let's go with blue. 3. Let Bn be equal to, we don't take the alternating portion. So the -1 to a power is not part of this. Bn is going to be the sequence of only positive terms. 1 over 3n plus 1. We can now say two things about this. We can say then Bn is decreasing. And next thing we could do is just take the limit of that thing. The limit as n goes off to infinity of Bn is a limit as n goes to infinity, 1 over 3 n plus 1. And this is a good time to just pause right here and mention, notice how many times these sort of limits come up all of the time. So it's really worthy to think about these shortcuts that we've been using to come up with the limits really rapidly, because this could save hours of your life of doing calculus work, reinventing the wheel on these things. Because the numerator is constant, and the denominator is of degree 1, this is automatically a limit of 0 on this one. Does that make sense to folks for that limit? Awesome. But if we got a limit of 0, and we know that our sequence of only positive terms was decreasing, this is what the alternating series test now says. The whole series has to converge. But it's not the strongest conclusion we want, because there's two kinds of convergence. That's kind of annoying with these sort of problems. But so far we can say, therefore, summation an, let me write this down, it's just for quick reference. This converges. And we said it's by the alternating series test when we indicated at the very start. But the larger question is, in the start of the problem, does it converge absolutely or does it converge conditionally? That's the next thing we need to resolve. Well, let's see, this is turning into a longer problem, so let's just put it on the next page. First one was really short and sweet, but some of these just take loads and loads of effort. There's not going to be a lot of these on a real exam, one at the very, very most. What makes this tough is if we're trying to determine the convergence, we now need to go to one specific test. We have to use, let's see where to go, absolute convergence test. We can't use the ratio test to determine absolute convergence because it failed outright. So we're going to see if the test is absolutely convergent by doing the following. This is called absolute convergence test. What we do in this one is we take summation of the absolute value of an. So writing that one out, here's an indicated. Absolute value is going to wipe out the alternating part. And so we have a summation as we go from 1 to infinity of 1 over 3n plus 1. So we need to test this new series. It looks like it's essentially a harmonic series in a certain sense, right? But there's a couple changes. Comparison test doesn't look like it's going to work too much on this one. So let's just go off to the limit comparison test. It was mentioned in class. That one's like a superstar as far as these two tests go. Comparison test is great if you can get it to work out nicely. If something just jumps out at you, or if you're faced with a series that has something like a cosine in it, you probably need the comparison test. But this test is a very, very powerful test in its own right. So let's just hit it with limit comparison and do the following, which means we're using a whole nother test. So let's say compare to summation Bn summation. The way we pick this one, we still have to give some indexing, going from 1 to infinity. We take the most important term in the numerator, not much going on, so we're just going to grab a 1. We look at the most influential term in the denominator. For very large values of n, it's just 3n essentially, very great approximation. The +1 has almost no influence when n is large. So we just take n itself. If you take the coefficient, no harm, but it simplifies the limit if you just grab n. So we're going to compare to this thing, which means we have to test that as well, but you have two options. Either say it's a p-series, it'll diverge as one, or just say it's the diverging harmonic series. So now that one's tested, we can now go down to limit comparison test. We have to indicate all these tests, but again, no harm if you put in massive shorthands. If you call this LCT, that probably works out as an acronym. We don't have anything else that could be an LCT. So if you throw weird acronyms at me, I could probably figure it out, especially if you're doing this in exam setting. No harm if you're taking some big shorthands. So limit comparison test, kind of like the ratio test, we take the limit as n goes to infinity of, here it's up to you. an or bn can go in the numerator, but recall we're testing absolute value of all the terms. So absolute value an goes above, divided by bn. So this is now a limit as n goes to infinity of, here's the an part, 1 over 3, n plus 1, multiplied by reciprocal bn, n over 1. Let's put the limit together as limit n to infinity, n over 3n plus 1. Good call, good time for a shortcut. Let's put a coefficient of 1 in the numerator just to visualize it. With a tie in degrees, the ratio 1 and 3 is the limit on this one. So we're ready to make a conclusion. If we're doing this particular test, we're not too worried if this came out as a 3 or a 5 or 5 billion. Everything's totally fine as long as it's positive. So our C value is on third, and it has to be a finite number, not an infinity. So because we have positive right here, we make this conclusion. Both series have to diverge because we said diverging on the one we're comparing it to. So one conclusion goes this way. Therefore, summation, absolute value of an, diverges. Then there's even another conclusion. Let's just write out another set of triangles. Why not? Bigger, because it's the bigger conclusion. We said that the original series, let's see, converges by the alternating series test. But when we put absolute values on it, it diverges. So therefore, original series an is not absolutely convergent. Let me control Z that real quick. Conditionally convergent. Again, tons of steps on this one, but once we go through a problem like this, think of it as one big review of multiple tests that we've used as ones and seeing how they work together. That's kind of the bigger takeaway for a problem like this one. Well, any questions at all, folks, on this weird series right here? Okay, well, we've resolved conditional convergence on this one. First one was absolute convergence by ratio test. And here's the last one in the notes. If you looked at that, what test would you say jumps at you immediately by the form of this series? Yeah, absolutely. The root test is what's going to do the job. And the indicator is right here. And no funny business with the exponent this time. This is like the best case for a root test. We can just apply it right as the series sits, no manipulations. So for that n right there, root test is highly effective. I don't want to say it's the only test you can use, but imagine trying to do the integral test on this. You have to integrate that with that x as an exponent. That's going to be a horrific kind of process. But if you go to the right test, really not too bad. Root test says to take the limit as n goes off to infinity of the nth root of the absolute value of the nth term in that kind of way. But looking at all of this, these things are all positive for every choice of n. So we're going to eliminate the absolute value. We'll just say we applied it and it's simplified. It's now the limit as n blows up to infinity of the nth root, n plus 1, 2n plus 1 to the nth power. So here's our next step, huge cancellation. And it's now the limit as n goes off to infinity, n plus 1, 2n plus 1. That limit comes out as a 1/2. Let's throw in a coefficient again, just to keep that visualization going with the notes. It comes out as 1/2, and well, if it's a half, is that convergence, divergence, or inconclusive? Anyone happen to know? Sorry, say again? Absolutely, this one would converge. Sorry about that. So we can now say less than 1. The less than 1 portion right here is absolute convergence. Well, we're done, folks. I mean, I guess I didn't exactly say the root test because in orange, that's meant to be a comment that you usually don't put on your homework. So we'll say absolute convergence by root test just to be safe. Well, we did, folks. This has been our rundown 11.1 through 11.6 of sequences and series. Starting in section 11.8, gets a little bit weird, but we're also heading towards our major goal, the punchline for why we did all of this kind of stuff. You'll notice there's almost no applications because the application is writing down a function as a new series called a power series. Any other questions, folks, before we go to those next notes?
So these ones are like power sets?
Not exactly a power set, no. By power series, what we mean is we're going to have x to power 1, power 2, power 3, power n generically. Power sets are another scary thing, for sure. I think I do remember those. Sounds like a counting thing, right? The set of all sets. Yeah, it's a nasty thing. So let's save this up. It's trying. There we go. And now let's go to the next section. So this section starts out with kind of a wall of text, but the reason for that is power series are kind of a lot different based on what we've been doing so far. So we kind of have to connect the dots of what we've been doing with what we're about to do. So when we say power series, this is what we mean. Cn is the coefficient of the power series, and it's called a power series because of x power n, or it could be x minus a to the power of n, for example. If you were to expand out this series, interesting things will happen. But first you'll get C naught, C1 times x, C2 times x squared, and so on. So this is just the expansion of the power series. It's a mathematical function now in the variable x. So we could write out this, for example. F of x as a power series would look like that. But when you think about it, in any algebra class, the moment you define a new function, you need to do one thing immediately, very important. You have to discuss what is the domain of that function. It's a set of all x for which this power series will converge. And we're going to discuss two things on these notes. So R will be the radius of convergence, and I will be the interval of convergence. So by interval of convergence, it could be something like this, from 2 to 3. By radius of convergence, we mean half the length of this interval. So the distance would be, let's see here, 0.5 for the radius. So if this is I, then R is 0.5. So that's a major thing that we're concerned about in this section. If you write down a power series, what in the world is its domain in the first place? It's going to be all x for which this converges, which means all of this stuff is on the table, but there's two tests that get used the most. Ratio test and perhaps the root test, if it comes up, are hugely used tests on these notes. Well, that's a power series here. This one we would say is centered at 0, because you could write this one, XL, as x minus 0 to the nth power, for example. This one here, just as good as a power series as any, we say this one is centered at A, or a power series about A, because of the A right here. So just a different power series. Example 1 is not really a problem that we'll do, but if we're talking about power series, it's just an excellent opportunity to talk about not the world's weirdest function, but one of the first truly weird functions discovered by Weierstrass back in the day. So this is called the Weierstrass function. It's an ordinary power series, but it's kind of a strange one with the cosine right there. And if we were to plot this, here's what it would look like. I didn't do this Desmos calculator, so someone else came up with this. But sorry, didn't mean to scroll. What's interesting about this function is it is continuous on the entire real number line, but there is not a single point upon which you can differentiate it. People didn't even know these things would exist, and people started finding them. So power series is one of those times where you start to realize the world of mathematical functions, just the ones we take with one variable, is actually a pretty crazy, scary place. There's a lot to say about functions. The world of functions are vast, very, very vast. So let's take a look at this. If I can open it, Control, click. There it goes. Hopefully there's no viruses on that. Might take a moment to load, and there it is. That's the Weierstrass function. This function is weirder than it even looks on the first look, but there's some information on the left. It's continuous everywhere, but not differentiable anywhere. It takes on this format, and you can play with these values here if you like. This is only an approximation to the Weierstrass function because C is the upper limit here. The true Weierstrass function goes off to infinity on this upper value. But another thing that's kind of weird about this is it's also a fractal. The hardware can't do it because it's not the best implementation with Desmos, but if you had a really powerful computer, you could code this up in Python or something. If you zoom in on this, it reveals the whole total graph again. This is a fractal pattern like the Mandelbrot set, for example. So this is one of the world's most bizarre functions, you'd think, but just Google weird functions. You'll find more and more bizarre stuff. Most of them are defined as some kind of power series, like these things we're studying right now. So our world of functions got humongous the moment we put these on the table. Let's try to find where Moodle is. There we go. And for first example we'll actually work on will be this one. Just some generic power series once again. Has a factorial in the denominator. It's centered about 3 is what we would say. Centered about 3. And all we're going to do with this one is just write down the first 4 terms. Seems like a sensible thing to do, whether we're doing a sequence, series, or power series. We have an abstract object. We should just dissect it for a minute. So indexing on this one starts at 0. That might look a little bit concerning, but here we go. At 0, we get, let's write it out this way, just to be a little bit more specific. We're taking the summation AN, and we're writing out x minus 3 to power 0 divided by 0 factorial. Already that probably looks a little bit weird, but let's keep on going. Plus x minus 3 to power 1, now when n is 1, divide by 1 factorial, plus x minus 3 to power 2, divide by 2 factorial. And here's the last one. X minus 3 cubed, divide by 3 factorial. Good call to put this at the very end, just as a personal reminder. This goes off to infinity. We're just approximating it with finitely many terms by writing down 4. But again, we have more to say because that probably looks concerning to us, right? Division by 0 is undefined immediately. But it just so happens, by convention with the factorial function, 0 factorial is defined to be 1. That feels really weird. Combinatorics can kind of resolve why we do that. 1 factorial is just 1. And if you say like 5 factorial, you're talking about 5 times 4 times 3 times 2. And we say times 1, again, weird because that doesn't affect the product. But this is the big giveaway or big takeaway. We're not dividing by 0 right there. That's a 1. There's more concerning stuff in here, but we'll get to them as we get to them. Let's keep on writing this out. That means x minus 3 to the power of 0, that's also 1 by exponent laws. This whole term is just a 1. Over here, this is x minus 3 divided by 1, so just x minus 3. Here we can start putting out 2 factorial is 1/2 times x minus 3 squared. 3 factorial, this whole thing turns into 1/6 times x minus 3 to the 3rd power, and then dot, dot, dot to say and so on. So let me hide theorem 3 for a moment. The bigger question now is, can anyone spot a number? You could throw x in there. You could throw in 4x that is a guarantee for convergence based on how we expanded out this sum. Let's go to a new page. So in other words, what does x have to be to guarantee convergence?
Here, or 3.
Good call. If you make x be 3, the first term, second term, third term, infinitely many terms are just annihilated totally. So the one value you have guaranteed convergence on is the number the series is centered on in the first place. So if we're talking about something centered at 0, plug x is 0 here, and it converges to C naught, whatever C naught is. Same idea on ours down here. For what number is x is this power series guaranteed to converge? Let's first put down the comment. A power series always converges at the value it is centered on. So if we have a power series centered at 3, like on this one, we have convergence on 3. Let's just write it out. At x equals 3, the summation an equals 1. So not super exciting in a way, but there's also a weird algebraic issue the moment we just said this. Our author talks about it and says we take certain things as a convention, we write down power series. So here's the weird stuff. If we say at x equals 3, we get a value of 1, notice what we're also saying. Right up there, you're putting in a 3 and you're taking 0 to a 0th power by default. Unless your textbook, whether it's calculus, engineering, chemistry, and so on, by default, we consider 0 to power 0 to be undefined. So that's a bit of a concern here, but whenever power series comes up in this situation, we do take this as a convention. Let's write it this way. In calculus, in the context of power series, we consider 0 to power 0 to be equal to 1. So that's our convention on something that is really truly kind of weird. In fact, let's play around with this thought a little bit before we get too far in the notes. If you grab a standard calculator, there it is, and you put in something like, say, 0 to power 0, let's see what it does. 0 power 0 gives domain error. It's essentially undefined. And again, that's a little bit weird. It's hard to explain why it's even undefined. But if you're super curious, there's a calculus 3 reason. There's actually two variables, a variable x for the base, a variable y for the power. And to make any sense of that, as x and y converge to 0 in the limit, this has to come out as the same number, but it doesn't. The rate or the direction your x and y's go to 0 affect the limit, and that's really kind of weird. But in power series, we allow that, and we call it a 1. Pretty weird. But any other questions so far about part B? Okay, really the two big takeaways of part B is, well, as far as the weird stuff goes, 0 factorial we consider to be a 1, and 0 to power 0 by convention also a 1. So going beyond that, what we're doing on these notes is just testing our power series for convergence and divergence. And it turns out there's a huge trichotomy for this, another one. So here's the next part of the notes. Theorem 3 says for a given power series, so here's one, we define R to be the radius of convergence, like we mentioned. I is the interval of convergence. And no matter what you put down on paper, only 3 things can happen, exactly one of the 3. So first part of the trichotomy, series converges only when x is a, where it's centered at. If that happens, we say the radius of convergence is 0. Instead of actually having a mathematical interval, our author says it this way, the interval collapses to just a single number, so we're writing it as a set containing just that one number, the value where it's centered at. So that a plays a special role in those 3 parts right there. So that could happen. Second thing that could happen is the series always converges. That's the Weierstrass function. That one converges for all values of x whatsoever, and there's plenty of other ones. So if the domain is all real numbers, we say R, radius of convergence, is infinity, and the interval of convergence goes from negative infinity to positive infinity. Now, honestly, that's kind of a weird interval, because oftentimes our author is going to use this to say negative infinity to positive infinity. That's the symbol for all real numbers, and the only reason our author is not using it this time is it could be a conflict of notation on that R, which has a totally different meaning. So for that reason alone, our author is only using interval notation, even when all real numbers comes up. So that's the second case. This is like the world's best case. You have a function you wrote down, and it always makes sense for any x. The third case is where we have to work a little bit harder. There's a positive number r, so you have convergence as long as x is a certain distance away from a. That distance is r, its radius of convergence. But then we have another problem that comes up. Knowing the radius of convergence won't tell you the interval of convergence. In fact, there's a bunch of possibilities, 4 of them. Your interval of convergence could be this. That means there's no convergence on the boundaries, just on the inside. So it's an open interval. It could be a half open interval. You have convergence on the left boundary, but not the right boundary. So the parenthesis here says it diverges when x is a plus r. So it could be the opposite situation, diverges on the left, converges on the right. Or it could be this situation. It converges for everything in the interval, including the boundary points. So we write it as a closed set in that case. And we have to test all those out. The way we test them is, if we're in case 3, we start using not the ratio root test, it's all the stuff up above we have to use. But when it comes down to it, if we're going to test that thing for convergence and divergence, all we're really using is ratio test to start out. That's such an important comment that we should say it right here. For power series, ratio test is, I don't know what the best word here is to emphasize, let's just say supremely effective. If ratio test doesn't seem to work, try the root test, let's say here, or root test. So we essentially always start out with ratio test or potentially the root test if we're dealing with a power series. What makes it a power series? The fact that there's x to a power and variable actually inside your series. Well, let's see, we've got, I think, enough time to try out just one. We'll come back on Monday. Just to recall, we're taking Halloween off since that's a very unpopular night class. I'll send out a reminder as well, just so we all are reminded of that. When we come back, we'll try out the rest, but let's start off with this one here. Any questions or comments, folks, before we begin? Okay, so right out of the gate, let's hit it with a ratio test. Which means we're taking the limit as n goes to infinity of the absolute values. Absolute values aren't relevant, excuse me. Yes, they are. If there's an x there, x itself could be positive or negative. Absolute values are absolutely irrelevant. So we're putting in an plus 1 in the numerator, divide by an in the denominator. This is a good step to write because it kind of centers your thoughts, tells you what you should be doing on the very next step, just by writing this alone. So now limit as n goes to infinity of the absolute value. For an plus 1, we're throwing n plus 1 everywhere we see n. So x to the power of n plus 1 in the numerator, n plus 1 times 3 to the power n plus 1 down below. We multiply by reciprocal of this quantity, so now it's n, x to the power of n. Hang on, let me try again. Almost had it. It's n times 3 to the power of n, divide by x to the power of n. So we'll do that limit there. And cancellations are pretty immediate on this one, but let's take an additional step just to show them. It becomes limit as n goes off to infinity, where we have xn plus 1, we can write that as x times x power n plus 1 down below. And same trick, we're just messing around with the exponents basically, so we can cancel faster. This is 3 times 3 power of n times n, 3 power of n, divide by x to the nth power. Now the limit is ready to pretty much give up its secrets because x to the power of n is gone, 3 to the power of n is gone, and what do we have left? N over n plus 1 and an x. Here's where it gets kind of interesting. Those absolute value bars pass right through n and n plus 1 because n is going off to infinity, but they settle right here. X is positive or negative, so we have to have an absolute value of x now. Its limit as n goes off to infinity, absolute value of x times n over, almost forgot let's distribute that 3n just to visualize it better. 3n plus 3. So that's the limit that we have to take. Back to could take the limit just right here, but here's another cool trick that could help out just visualizing it. Anything that involves n is kind of trapped here. I can't take out the 3 as well, it's just trapped in the denominator. But that x is not indexed by n at all. With regards to a limit as n goes off to infinity, absolute value of x is constant. That means, in the limit laws, absolute value of x can move in front of the limit. So now we're just focusing on the limit as n goes to infinity of n over 3n plus 3. Makes the visualization just a little bit nicer. We'll throw a coefficient of 1 on that n. because now there's a tie in degrees, and so we get absolute value of x times 1/3. Well, let's keep on going. That simplifies to absolute value of x over 3. And then from here on out, we do something that's a little bit different because we're dealing with a power series. We're trying to find all x for which this thing converges. Because we're going for convergence as our conclusion, in the ratio test, we insist it's less than 1 in the limit and solve for all x's that make that true. So here's the interesting part of how we're using the ratio test. We go less than 1 because this part gives convergence. So next step, if the absolute value of x divided by 3 is less than 1 for convergence, that then implies absolute value of x less than 3. This alone gives us radius of convergence. The radius of convergence r is 3 now. Next thing we're going to do is we need to come up with the actual honest interval of convergence. So we do the next thing. Sorry, I'm having trouble with those slashes there. So next step, take this interval and just eliminate absolute value. You get this next thing algebraically. This would imply -3 less than x less than 3. And here's the next kind of a sad fact about the ratio test. When the ratio comes out as 1 in the limit, the test has failed in the sense that we have no information whatsoever. When would it come out as a 1? That's if you put a -3 here, that's exactly 1. If you put +3 here, it's exactly 1 as well. So back down to here, ratio test fails at the boundary. Values -3 and 3. That's super unfortunate because what does that mean? If it fails on the boundary values, we have to test the boundary values. So we know it converges between -3 and +3, but we have no information on -3 or +3. So here's our next step. We need to be looking at this, so I'll take it down as a screenshot. And we say the following. Just for the sake of the notes, we should say this keeps on continuing. And now at x equals -3, we need to rewrite our series. Recall it's a power series. You're allowed to do this. You can plug in any x and ask if it converges or not. But by the ratio test, we do know it's going to diverge if you're below -3. We already know that. We know it'll diverge if it's above 3. What we don't know is what happens at the boundary values. So we test directly at -3. That means our summation an becomes a summation as we go from 1 to infinity of take that -3 and just plug it in right exactly there. -3 power of n divided by n times 3 power of n. These things can cancel off and leave summation n goes from 1 to infinity. So you could bring both the -3 and the +3 into a fraction, both raised to power of n. But then that's a cancellation. It's just -1 to power of n. Divide by n. Let me highlight that there. Does that make sense to folks on how these two can cancel and become the -1 power n? Okay, once we got there, do we really need to test it? We could use the alternating series test, but that one has a name. This one is the divergent, excuse me, let me back that off. It is the convergent alternating harmonic. I'll abbreviate harmonic to just harm series. There's two named series. The alternating harmonic one converges. That means -3 is in our interval of convergence. But we still don't know about +3. We need to test that one out. So one more test. At x equals +3, summation an turns into summation as we go from 1 to infinity. Always good to look at the original series here. In place of x, we throw in a 3. Now it's 3 power of n divided by 3 power of n. But this is a nicer cancellation. This just turns into summation from 1 to infinity of 1 over n. And we know the punchline to this one. This is the diverging harmonic series this time. So we'll say diverging harmonic. I'll put a S dot for series. Keep on running out of space there. So let's take a look at and reconvene. For our final conclusion, we wanted two things. We wanted a radius of convergence. I'll just restate it here for reference. And we want an interval of convergence. This is the domain of the function. So the interval of convergence at -3, it converged. So we'll go bracket -3, bracket only because we said converges. And at +3, it diverges. So we go here. The parenthesis throws +3 out of the domain of the function. And now this is that domain. Let's say it right here, just to finalize this, just as a reminder. The domain of f as a power series. Well, we did it, folks. What we're essentially saying is this power series is a real mathematical function, just like, say, cosine x. No different. What is different is its domain is a little bit weird. Bracket -3, all the way up to +3, but excluding it with a parenthesis. Strange domain, but that's what we're going to be getting into more and more. Alternating harmonic series and the harmonic series, they come up a lot in the notes. So those are almost like freebies when it happens. No complicated test is necessary. But I think this is a good stopping point for us. We have less than a minute. Any last questions or comments then, folks, before we call it a night officially? Exactly. Radius and interval, and that's the punchline to the whole set. Well, have a great night, folks. Have a safe Halloween, and we'll come right back to these notes on Monday's class. And by the way, for the folks thinking about exam 3, because we didn't finish 11.8 this week, next week we'll finish it, but it's not going to make it onto the third exam. Third exam is going to start section 9.5, go up to 11.6. So that will be the cutoff. I'll start putting in this information pretty soon over this upcoming weekend. But have a great one, folks. I'll see you all later.